Hi, welcome to week 4 of Physics 20. This week we're going to talk further about energy and work and how they're related to each other. So to start off, let's talk about the two different types of energy we're most concerned with, and that's kinetic energy and potential energy. So kinetic energy we know is 1/2 mv squared. Kinetic energy is measured in joules, mass in kilograms, v in meters per second. Now if we look at what happens if the speed is doubled or tripled, we see that this relationship is a little bit different than if just the mass is doubled. So I have 1/2 mv squared. If I were to just double the mass, so if the mass were to be doubled, there's a direct relationship between mass and kinetic energy. So if the mass goes up by 2, so if I have 2 times the mass, I have 2 times the kinetic energy. If I have half the mass, I have half the kinetic energy. So there's a direct relationship between mass and kinetic energy. If the velocity changes though, because velocity is squared, that relationship is different. Right? If I were to double the velocity, so this is 2v. So I would have EK is equal to 1/2 m. Now this is 2 squared, so that would be 4v squared. So I have everything else the same, 1/2 mv squared. If I were to just double the speed, my kinetic energy changes by 4. So I get 4 times my original 1/2 mv squared. So there's a squared relationship between velocity. So changing the velocity is far more impactful in the kinetic energy than changing the mass. Here's a quick question. Maybe pause the video and answer it. We have a 21 kilogram coyote. I researched that. Falling at a terminal velocity of 55.4 meters per second. I researched that as well. We want to know the coyote's kinetic energy. Let's pause the video and answer this question. So my kinetic energy is 1/2 mv squared. It's amazing how it just appeared out of nowhere. If I put that in my calculator, I get 3.7 times 10 to the 4 joules. Or I could say 37 kilojoules. The other type of energy we want to talk about is potential energy. And if you think about holding a ball, there are certain things that would actually impact the amount of energy it has, right? We know it has energy because when we let go of it, it falls. If we were to drop it from a really high height, it might hurt us. So the height is one thing that actually impacts potential energy. The mass of the object does as well. If I have a bowling ball, that's going to have more energy than a golf ball. I would be a lot more scared standing under a bowling ball than a golf ball. The other thing that's important is the rate at which the object is accelerating. I shouldn't say speed, just say rate or acceleration. And that is g, 9.81 meters per second squared. It would probably be more terrifying if I was on the surface of a neutron star, where g is a lot higher. So potential energy in joules is equal to mass in kilograms times g in meters per second squared times height in meters. Now you can see again what the fundamental units of a joule are. A fundamental of a joule is kilograms times meters squared over second squared. Those are the same thing. We looked last week at work and how changing the height of something actually does work and what that means. So we know work is force times distance, and we know that force is mass times acceleration. And for things that are accelerating due to gravity, this would be mg. So if I multiply that by distance, which talking about going up and down is probably the same as height, work is equal to mgh, or it can be the change in energy, in this case the change in potential energy. Here we have a coyote again, 21 kilogram coyote, 187 meters off the ground. Calculate how much potential energy the coyote has. So we do this calculation. And we get 38,523 joules, or 3.9 times 10 to the 4 joules. Or I can write that as 39 kilojoules. You'll notice that there is a direct relationship between all these variables. If mass goes up, potential energy goes up the same amount. If the height goes up, potential energy goes up the same amount as well. And if we were to somehow increase the gravitational field strength, potential energy would go up by the same amount as well. So it's not a squared relationship like it is with kinetic energy. Here's a question. If you got hit in the face, how fast would the ball be moving when it hits you? So in this video, there's probably different ways to do it. I think probably the one thing we are going to ignore is we're going to ignore this initial x velocity, which we probably shouldn't. But we know after looking at projectile motion that it's actually going like this. And actually, maybe that's this week's assignment. If you want, well, you'd need to look up like what the average speed that someone can throw a basketball at is and find out how fast it actually is going when it hits the ground. We are going to just look at how fast it's going in the vertical dimension. So things we know in order to help us solve this problem. If I am throwing this ball off the top of this tower, at the top, it has potential energy. As it falls, that potential becomes kinetic energy. Now, energy is one thing that, especially when we're talking about gravity, that is conserved. So my potential energy at this top, the same amount of energy is present at the bottom, it's just all become kinetic energy. So we know that potential energy is equal to kinetic energy at the bottom. Potential energy is mgh. Kinetic energy is 1/2 mv squared. We can get rid of mass. And to find v then, we have 2 times gh. We move that over. And then I need to square root it. So things I need to know to help me solve this problem is I really just need to know the height. And if you're using kinematics, it would be the same thing, right? Our initial velocity is 0. We know our acceleration. The thing that we need to know is the distance and how far it's falling. The idea here is that potential at the top equals kinetic at the bottom. As long we don't need to know the mass. We need to know the height, so 170.98 meters. That's how high this tower is. So that's our height times 9.81 times 2. And then I square root it. And we get 58 meters per second, which seems very fast. 367 times 3.6, 208 kilometers an hour. Probably are ignoring air resistance a little bit too significantly. But we're ignoring air resistance. Now, as that ball falls, gravity's doing work. So work energy theorem, to revisit it, is the idea that work and energy are related. So work is a change in energy. If I have kinetic energy initially, and then afterwards I have more kinetic energy, well, I need to do work in order to change that kinetic energy. So if I want to increase or decrease the energy, whether it's potential or kinetic, I need to do work. So some things that change when we do work is there is a change in energy. So my work could be my final kinetic energy minus my initial kinetic energy, or 1/2 mvf squared minus 1/2 mvi squared. That could be my work. Which is same as force times distance. Maybe we can get crazy with this. Let's do it. Force is mass times acceleration times distance. 1/2 mvf squared minus 1/2 mvi squared. Don't need any of those masses. I can maybe multiply everything by 2. I'm going to move up to the top here. 2AD is equal to VF squared minus VI squared. So I get VF squared is equal to, I move VI squared over there, VI squared plus 2AD. Hey, there's a kinematics equation. The idea here being that, just like last week, we can use energy or we can use kinematics. The nice thing about physics is that it's universal. Okay, here we have a sled accelerating downhill from rest to 1.6, and we want to find the net work done by gravity on the sled. You can use kinematics, let's use energy. Work is a change in energy. At the top, the sled had some potential energy. At the end, the sled had kinetic energy. There is a change in energy, and that's equal to the work. I don't know how I would calculate the potential energy at the top. I don't have enough information, but I can calculate the kinetic energy at the bottom, and those two should be the same. It's just this type of energy has become this type of energy with the help due to gravity. So my work is my kinetic energy at the end, which is 1/2 mv squared. So 61.5 divided by 2 times 1.6 squared is 80 joules of work. And because it's going down, gravity's going down, and the energy is changing in that direction, that would be positive work. So lots of questions this week dealing with conservation of energy, revisiting work questions. These are work questions. Energy theorem. So these are energy. But as you work through these questions this week, if you do have any questions, feel free to post them in the stream and we will answer them.